Hi students, this is part 3 in traffic simulation series of videos. In the first video we discussed, I have given a generic introduction into traffic simulation, its need and the various steps involved. In the second stage we were discussing on the model development. So now we will move on to the details of model development, headway distribution, and then we will be seeing the model validation, calibration, and the error check. So all this will be dealt in this video. Welcome you all to the video. We discussed about the overall framework for the microscopic traffic simulation, which starts with providing input to the model, then vehicle generation, which depends on the headway distribution, then comes the placement of vehicle into the study stretch, and then vehicle movement is controlled by two theory. One is car following and another one is lateral shift theory, and then this process is repeated until the simulation time is over. So now let's go and see the details about the vehicle generation step. Now let's see more details into the vehicle generation module. Vehicles are generated according to a kind of distribution. It can be based on the vehicular headways or it can be based on the vehicular arrival patterns. Then headways generally follow any one of this distribution based on the flow rate. If the flow rate is low, then it follows negative exponential distribution. Whereas if the flow rate is high, it follows normal distribution. If it comes in between, if the flow rate is intermediate, then it follows Erlang distribution. So based on the vehicular headway distribution or based on the vehicular arrivals, the vehicles are getting generated. So let's see the details of that. Let's see how the vehicles are getting generated if the headway follows negative exponential distribution. The probability density function of exponential distribution is given as follows. We have already studied this. And then the cumulative distribution function is like this. And if this is the case, from the above equation, the expression for exponential variate headway x, it can be derived as follows, where in this expression, mu is the mean headway and r is a random number which comes in between 0 and 1. And the random number generation is an essential part in any stochastic simulation model, especially in the vehicle generation module. So there are numerous methods available, or there are numerous methods in terms of computer programs have been devised to generate this random number. Therefore, headways can be generated using the above expression by giving a random number and the mean headway as an input variable. We can go for generating the vehicles. So let's see more about the random numbers. What are random numbers? So random numbers, they are sets of digits which are arranged in a random order. Because they are randomly ordered, no individual digit can be predicted from knowledge of any other digit in the group. Okay, so computers can generate truly random numbers by observing some outside data. Say it will be observing some mouse movements, or it will be getting input from the fan noise, or which is not predictable, and based on that it will be creating data from it. So this is known as entropy. And other times they generate random numbers by using certain algorithm so that the results appear random even though they aren't. So it is following an algorithm. Okay, so because of that it is not really random. Again, we call that to be random numbers, or we call that to be pseudo random numbers. So random numbers are numbers that occur in a sequence such that two conditions are met. The first one is the values are uniformly distributed over a defined interval or set, and the second rule is that it is impossible to predict future values based on past or present ones. So random numbers are important in statistical analysis and probability theory. So most simulation are random number driven, and in such simulations random numbers are used for the inter-arrival times, service times, allocation amounts, and routing probabilities. So for each application of random numbers in a simulation, a distribution must be chosen. So let's see a video which explains about the random number generation and random number.
Hello and welcome to Curious Thought. Today we're going to be talking about random numbers, specifically how they are generated. 5, 9, 17, 2, 13. Humans are really good at generating random numbers. We can list off endless amounts of them and no apparent pattern. We're unpredictable. Computers, however, are a completely different story. You see, a computer is actually incapable of doing anything randomly. All they can do is follow instructions, making them completely predictable. So how can a predictable machine generate unpredictable numbers? One way is to use external sources as an unpredictable factor. Scientists can't predict atmospheric noise at a certain moment or when radioactive decay occurs, so they're basically random. Computers record data from these unpredictable sources, effectively giving them what they need to generate random numbers. This method is called true random number generation. The alternative to this is pseudo-random number generation. Now, this method is much more efficient than generating true random numbers as it requires no external data. But pseudo-random number generators aren't actually random. They just look random. They start with the seed value and then run it through some sort of algorithm to generate a number. And modern algorithms are so developed that it's virtually impossible to tell that they're not actually random. So, which is better? Well, it depends. If you're playing a video game, pseudo-randomness, being much quicker and more efficient, would work much better. It doesn't matter that the randomness isn't actually random. It just needs to seem random. But then take the important role of random numbers and data encryption. If a hacker figures out the seed value in the algorithm, they can break your encryption. In this case, true random numbers are much better because they can't be guessed by hackers.
In a similar way, the vehicle generation can be done based on the vehicular arrival pattern also, and this vehicular arrival can be modeled using the Poisson distribution, and the mass function or the probability mass function of Poisson distribution is given here, where Px is the probability of x vehicle, say n number of vehicles or x number of vehicles arriving in an interval t, and lambda, it is a mean arrival rate of vehicles. So we can use the Poisson distribution also for vehicle generation. Now let's do a numerical example. What is given here in the question is you are provided with a flow rate. So 900 vehicles are arriving at an interval of 1 hour. So in 1 hour, 900 vehicles are arriving. So you are asked to simulate the vehicle arrivals for 1 minute using negative exponential distribution. So here they are assuming it is a low flow rate condition. That is why the headway is, they are saying like the headway can be modeled using negative exponential distribution. So the first step involved here is we need to calculate the mean headway. So in an hour, 900 vehicles are coming. So what is the headway between them? Which we can calculate. The mean headway becomes 4 seconds. And next step is we need to calculate we need to generate, it's not calculation, we are generating random numbers. So if I am asking you to give me a random number, you can simply say. But that's not the case with the computers because it works in a predictable manner. Okay, so we are giving some instructions or we are giving some algorithms, accordingly it will be predicting. So here also the computer, it will be generating a random number. We can generate a random number varying from 0 to 1. So the random numbers generated by computers are based on certain algorithms. So that is why it's known as pseudo-random numbers. So next step is generate any random number between 0 and 1. And third step is calculate the headways and then we can estimate the cumulative headway. So these are the three main steps involved in this simulation process. Let's see that in detail in the next slide. Next, we can get the expression for exponential variate headway x, which is following the negative exponential distribution. So if we use the PDF of the negative exponential headway, we will be getting the expression for the headway x, or it is the exponential variate headway x, and from that we can find out at what time different vehicles are arriving. So let's consider the first vehicle. So for the first vehicle, let the random number be any number which comes to your mind between 0 and 1. So let that be 0.73. So if you are doing this in the computer will be generating this random number. So let's assume that the first random number is 0.73, and if you put that value in the given expression for the headway variate, then you will be getting the corresponding headway value. So the first vehicle will be arriving at 1.23 seconds from 0th time. Then let's consider the second vehicle. Second vehicle, let the random number be 0.97. Then the x is 0.14, or the headway is 0.14. then what will be the cumulative headway? It will be 1.23 plus 0.14, 1.37. So in a similar way, you can calculate at what time different vehicles are arriving at. So based on the random number, we will be calculating the exponential variate headway, and then we can take the cumulative headway, which will be giving you the arrival time from the 0th time from where we are starting the simulation process. So this is how we can arrive at the arrival times of different vehicles in the traffic stream. Next, we can have a problem where the hourly flow rate again the same 900 vehicles per hour. Then we are asked to do the Poisson distribution. So using Poisson distribution, we need to model the vehicle arrival for 10 minutes. So that's a problem. So the first step here also is to find how many number of vehicles arrive in a minute. So 1 hour 900 vehicles are arriving. So we can say in 1 minute how many vehicles are arriving. But if you need, you can find even for lambda to be in 1 second. Accordingly, we have to do the calculation. So if it is for 1 second, we have to do that many number of iterations to take it to 10 minutes. So if it is 1 minute, we can do 10 number of iterations and finally get that. So it's easier to get the number of vehicle arrivals per minute because number of iterations will be less in that case. So you can find what is lambda, which is 900 vehicles. If it is arriving for 1 hour, then we can get how many number of vehicles are arriving in a minute. And after that, we need to get the probability that this many number of vehicles are arriving in a minute. Using Poisson distribution, we can find that out. So once we get the Poisson distribution, we can generate the random number and we can see like if this is a random number, how many number of vehicles will be arriving at based on the Poisson distribution. So let's see that in detail in the next slide. And now let's see the vehicle arrivals using Poisson distribution. So we have the scan interval. We fix the scan interval to be 1 minute, and the total simulation time is 10 minutes. That's what is asked with the question. So for 10 simulation or 10 minutes of simulation time or simulation duration, we are considering 1 minute to be the scan interval. So every 1 minute, we need to get how many number of vehicles are arriving. So for that, what we can do is for every minute of scan interval, we can get the corresponding random number. We can generate a random number. So a random number, it usually varies from 0 to 1. So according to the random number, we need to get how many number of vehicles are arriving based on the Poisson distribution. So this is the probability density function of Poisson distribution, and we can use this to get how many numbers of vehicles are arriving. So we can use this to find the Poisson distribution. You can get the PDF as well as CDF, the cumulative density function, or you can find the cumulative value for that. So for the one number of vehicle, how much is the probability? Two number of vehicles, the probability, 3, etc. And the next column, the third column is representing the cumulative one. Okay, so adding it up, we will be getting the cumulative frequency. Okay. Then what we can do is for the first scan interval, the random number generated is 0.231. So accordingly, you can get a corresponding see how many number of vehicles are there for this probability of 0.231. So here in the Poisson distribution, you can see here that is 0.231. The cumulative distribution, if you see 0.231 comes somewhere here, right? So accordingly, you can get say 4.18, 185 is 11, 4.268 is 12. So accordingly, we can get how many number of vehicles are arriving there. In the second scan interval, we are generating a random number of 0.162, and from the Poisson distribution, we can get how many number of vehicles are arriving. So in a similar way, we can find out how many number of vehicles are arriving, and based on the random number generated, we can associate that with the probability density function, or we can associate that with the probability of arriving that many number of vehicles, from which we can get the number of vehicles arriving in each of these scan intervals. So that is how we are getting the total number of vehicles arriving during the 10 minutes. Is you can add it up, which will be 143. In a similar way, you can go for finding the negative exponential distribution that we did in the previous case. You can see you can continue doing that, and you can see like for 10 minutes how many number of total vehicles are arriving at. It will be more or less same. There will be some difference because the random number, it was randomly generated, so we don't have any control over that. So there will be a small difference between the final answer you are getting, but even then it will be somewhere around 143 vehicles itself. So this is how we can generate the vehicles based on either headway distribution or based on the number of vehicle arrivals. Hope the concept is clear to you. Thank you.